Hello everyone. Today I'm going to talk about how you can track mitochondria and their movement, including the fission and fusion events. As you can see on this small recording, that there are fission-fusion events going on, and when one mitochondria fuses into another, the tracking ID, for example in this case 57, track ID 57, goes along with the fissioned mitochondria, as you can see up here. So I will show you how you can track your mitochondria using a very simple plugin in ImageJ that is very useful so far, and you can also analyze the speed, the directionality, and various other components that are suitable for scientific analysis of mitochondria. Over here you can see that I have opened several images that I have taken from live cells, and these are time series, as in several images were taken over a 5-minute period, and I would like to analyze the movement of the mitochondria as well as the fission and fusion events that are ongoing in these mitochondria. So how do I go about doing that? So first of all, I'm going to take one of my cells and crop that cell, and I'm going to duplicate it and close my other windows. This is going to undergo deconvolution, and if you don't know how to do deconvolution for your images, please refer to my other videos. I'm doing 100 iterations, and this can take up to 1 minute or more. Therefore, I'm going to pause this video and come back. Okay, so the deconvolution has finished, and here's the output. So you can see the side-by-side comparison before deconvolution here on the left, this one, and after deconvolution. So deconvolution does a lot of different things. You can watch other videos if you are interested in learning. I am at this point more interested in showing you how to track mitochondria and to ascertain different parameters of mitochondria. For example, pay attention to this area. You can see the movement and the vibrations of the mitochondria. They're changing very rapidly. In fact, the whole cell is moving, but by looking at the fission-fusion events, such as the ones that are going up there, you can try and ascertain some really cool, neat information about the dynamics, the intracellular dynamics of cells and mitochondria. Okay, so my goal is to show you how you can track and use this information. Now, to keep this analysis a little bit computationally on the light side, I'm going to just crop out this area. It looks very interesting, and yeah, it looks very interesting. There's a lot of stuff that's going on. I'm just going to crop this area out by duplicating just that area. So this gives me a little bit of padding on the edges. Okay, so at this point we are purely going to be relying on thresholding. You can do thresholding in many different ways. For the demo purposes, I'm just going to show you just the simple thresholding. And before I even do thresholding, I'm going to take my image and do some background subtraction. Now you can decide and play around with what type of algorithm you want to use for your thresholding and all kinds of other things. For my demo here, It really doesn't matter which thresholding parameter I use. So let's just go with this one, convert to mask and create a new stack. Okay, so this is my thresholded image. I'm going to pass this in a plugin called TrackMate. And if you don't know TrackMate, you can go to the ImageJ plugins and find TrackMate. If you need more information, you can find more information in the ImageJ documents, and it's a really useful tool to track splitting and merging events, such as the ones that are being shown up here. There's one cell that comes and duplicates and then merges together. So those type of events that are hierarchical based, in which you need to track the precise movements and also whether certain events are taking place, such as fission and fusion. And this is really good. Highly recommend using this. So let's go on and see how this works. So when I open up the TrackMate, it will take the image that I have on display, or the current selected image, and pass that on into TrackMate. For me, these are time series video recordings, and therefore it has converted my Z stack to a time t variable. So without changing anything, I'm just going to move on to this. You can do manual thresholding detection, which is built into TrackMate. But if you are like me and you're using external thresholder, such as MATLAB or Mathematica, to threshold your images, and you have a personal preference for using thresholding outside of ImageJ and then bringing a mask into ImageJ for analysis, you can certainly choose the mask detector, and it will allow the TrackMate to interface and pick up on the masks that you're passing in. So when I do the mask detector and I click on preview, it has simplified the regions by drawing a contour map on top of my my mask, thresholded mask. Now if I unclick this simplify contours, it is picking up every single contour, every single nook and cranny of my threshold image, and that is not what I want. I want the contours to be simplified because they're easy to look at that point. So for me, I'm going to click the simplify contour and hit next, next again, and over here you can decide what type of quality you want for your data. Now for me, I want all 710 spots that I have in all of my images to be used for analysis purposes, because I'm assuming I've done thresholding outside of ImageJ and thresholding is really good, so I'm happy with it. So I wanted to analyze all 710 spots that it has in this mask. So for me, I'm not going to change this, so just keeping it at the maximum level so I pick up on all of the 710 spots. And over here now in this category, you can filter out certain variables. So for example, I want to keep all mitochondria that are greater than let's say 4 or 5 pixels. So maybe like 20, no, maybe like 4 or 5, somewhere around here, like 5. Okay, so I want it to filter out anything that is smaller than 5 pixels. So I can decide by moving this graph around as to what size mitochondria I want for it to analyze. And then I'm going to press next. Now this is a little bit application dependent. Depending on what you are applying TrackMate to, you can decide on what type of tracking you want. For me, I wanted to track overlapping events. So for example, two mitochondria, when they fuse together, I wanted to be able to track the fission and fusion events. So I'm going to keep this tracker, which can allow me to track unions of different tracks. So just keeping this as it is, you can decide and read about different trackers to see which algorithm works best for your application. For me, overlap tracker works best. I'm going to keep it. Again, play around with these scale factors and those type of things that are very situational specific. Therefore, I'm not going to spend time on this. You can read when you do your own images and you run those through TrackMate. On the next screen, it has taken about 1 second to generate all of the tracks for these mitochondria. So it's showing me that this mitochondria, for example, is moving from that area to this area. So I'm going to very quickly edit. And the things I want to edit are the tracks. I do want it to draw tracks, but I want it to draw tracks forward in time. And the minimum I want it to display is 1 and maximum 5. And I want the fade time to be 5 seconds. My interest is in finding out how many times these mitochondria are splitting. So what we have to do now is, since we have these tracks, we need to be able to merge them together and keep track of a single ID that is associated with the biggest mitochondria, so that anything that gets merged into it gets that same ID number, and when the fission happens, that the track ID will continue with the daughter but in a different way. So that way we can track the number of events that are taking place. Alright, so to do that, I'm just going to press continue, continue, continue until I get to this select an action screen. So in select an action screen, I want to do several things. So the first one is I want to do spot auto naming. And the convention I would like to use for spot auto naming is append AB for each branch. Excuse me. For each branch. And you can read about what this does. So it will make a lot more sense once I show you what this is going to look like. So the other thing I want to do is I want to generate now a new image which has tracks. For example, I selected track 1, and now I'm going to take you through each of the frames to show you how it's keeping track of track number 1 and everything that merges into it, and everything that splits off from it. So there's the first merge event, and after that first merging of these two mitochondria right here, the top one has gotten the letter B attached to it, and the bottom one has gotten a letter A attached to it. And this convention is to denote whether the mitochondria that is splitting or merging is coming from the left side or the right side. And now you can see that that track is labeled track 1B again because it has all merged into the right side of the track. And now this one here is track 1.bb, whereas this up here is track 1.ba. So what this is denoting is that this track was track B that has split off to the left and has become track 1A, and this was track 1B, but it has split to the right, so now it gets a denotation of B. So this allows us not only to determine the number of tracks and the splitting and the merging events, but also the directionality of those splits. So this is just visually, you can verify that this is all taking place. And now let's go back to the tracks here, and you will see that the information in these files have updated. Now we have track 1 through 25, that's 25 mitochondria that it has tracked, and for each of them we have very specific information listed. Mean speed of that one mitochondria, for example, the one that's up here, which is track 0, and it's actually this image. So track 1, that's track 1. It gives me so much information here, where the track starts, where it stops, track distance, for example, in pixels, the mean speed, the maximum speed, min and median, and all kinds of other information. It also gives duration and displacement. Somewhere over here it should give displacement and other quantitative, qualitative, and quantitative outputs. Total distance that this mitochondria travels in pixels is 324. This is not displacement. If you want displacement, that would be somewhere on another file. Displacement. So for track 1, you can take all of your track 1 files from here to all the way down to wherever the track 1 goes, right there, and you can see all of the displacements for each individual splitting mitochondria, each splitting daughter mitochondria, because it tells you right here all of the splits and the directionality of those splits that are taking place. The other easy thing is that you can export all of this data to CSV file for any kind of other processing that you want to do. Okay, so this video is getting really long and I'm running out of time. The last thing I want to show you guys is that you can compute distances to ROIs. As in, let's say I want to figure out how close or how far apart are these two mitochondria. I can do that very easily by doing this computational action in TrackMate, going here to compute distances to ROIs, but you do need to have the ROIs selected. And the way that you can do that is again by going to tracks, and let's say I want to, this is my track number 1 and this is my track number 2. I will select those two tracks. And I will create ROIs for those tracks. So I have just gone on to create ROIs for just track 1 and track 0, which are these two mitochondria. And in my ROI manager, now I have all of those individual tracks from each of the frames. Now if I go and do the compute distances to ROIs, computational distances for visible spots to closest ROIs have been completed. And now I can extract that information by going back here to tracks. So this column has been generated as the distance to ROI, and these are all distances in pixels. Okay, so I hope this is helpful to all of you.